and it's all about neural network stuff. So hopefully it's interesting. Hopefully, I don't know, you get some satisfaction out of doing your homework. And that's that. Okay, we're starting a new topic this week, a little bit, I guess. Well, not this. We're going to take a look at some maximum likelihood estimation, which I know is covered in other classes, but I guess I want to cover it too, and we'll take a look. So first, we're going to use maximum likelihood estimation for linear regression. And so first, it helps to take a look at linear regression. We'll look at least squares regression, and then we'll reframe the same problem, but as a maximum likelihood thing. Okay, so this is all review. This is where we've been, and we said when we do linear regression, we say our predicted line t hat is W transpose xn. Okay, so for each observation in the nth observation, t hat is W transpose times the nth row in X. Okay, and if you want all of them, you just do W transpose X, and you'll get kind of your column vector of prediction values. Okay, and so the relationship, well, this just tells us that the relationship between T and X is linear, although it does not necessarily mean that T has to be a straight line per se. Okay, and that the variables in X, you could have multiple columns in X. Some of those columns in X could be like polynomial, factors of X and things like that. It just means when you calculate your predicted value t hat, you're taking whatever value in X and it gets multiplied by a constant W. Okay. All right, anyway, the way we figure out what W hat should be is we say we need the W hats so that we minimize the mean squared error, the difference between the actual value and the predicted value. And that is to say this mean squared error can be calculated by doing T minus XW, transpose T minus XW, and we say we want to minimize this total value, find the W's that minimize this. That's going to be our W hats, right? We're comfortable with this argument over W terminology notation, okay? Just means find the W's so that this quantity is minimized. And so when we train the linear regression model, that is, we are looking for those values W, it's basically the same approach that we use for training a neural network or anything else. We define a way for a model to make predictions based on the inputs X and model parameters W, and that in this case, it's very simple. We just do X times W. That's how we get our predictions. For a neural network, it's a little bit more complicated, right? It's X times W, and then you apply an activation function. You multiply it by another W and apply an activation function or something like that. But there's just a sequence of things that take your inputs, your parameters W, to get your predictions. We have a loss function, and then we estimate the model parameters by figuring out what values will minimize the loss function. We can do this using calculus, or we can do it using gradient descent. And that's what we've done so far. It's all about been minimizing the loss function. That's been our objective function, is this sum of squared errors or mean squared error, and we're saying let's make this as small as possible. What we're going to do today is we're going to do a different approach. We are going to say let's maximize the likelihood. Okay, so we're going to change our objective function to be a likelihood function, and we're going to say what values of W will maximize the likelihood. Okay. Does anyone want to tell me the difference between probability and likelihood? Probability versus likelihood. Okay, maybe an easier, so they're both probabilities, but a probability function is different from a likelihood function in what ways? So when you put in, what do you plug into a probability function? You guys are breaking my heart. You're what, third-year statistics students? You're going to graduate in a year? Okay, all right. So for a probability function, the value you plug in is your random variable x, right? You plug in, you say, what is the probability of getting this value? And it says, this is the probability. That's your probability function, okay? And what's the rule? That if it's a discrete thing, if you plug in all of the possible values of x, what do you get? It's going to add up to 1, right? And if it's a continuous thing, if you integrate across all possible values of x, it integrates to 1, okay? All right, in a likelihood function, what is the thing that you're plugging in? So you're not plugging in your random variable x. You're plugging in a parameter of kind of your probability model or something like this, right? So your data is treated as fixed, and then you say, what's the likelihood associated with this particular parameter value? Okay. Here, we'll do some examples. Maybe that'll make it a little bit better, okay? And that's kind of the central idea behind maximum likelihood estimation, which you've seen already, I hope, 100B and stuff, right? So does this look familiar for maybe this is from 100C, I don't know. Talking about linear regression, we're saying your actual values, not the predicted values. The actual values is W transpose X, basically the linear component plus random error. Yes? Okay, and then we often model the random error, the random noise, as coming from a normal distribution, a Gaussian distribution or something. But I guess you could choose other things as well. Okay, so we're going to say this is how we get the actual values in our data set. And the only difference here, okay, between what we had before is that we have an E component. So basically, we're saying the actual values is the difference between T hat plus some random error. Okay, and right now T hat is found by doing W transpose X sub n. Okay, so this is all we're saying. Okay, this should be T hat sub n. But so the actual value is the prediction plus error. Okay, and I think that's very familiar to all of us. Okay, but the key here is now that we've included this random noise, okay, this whole thing becomes probabilistic because a probability distribution describes what our random noise looks like. Okay, we have some kind of probability distribution associated with the random noise. That's basically what it means to be random. If it's random, there's some kind of probability thing associated with it. And so now we have a probabilistic model. And so what we do is when we look at our observations, we say our observations come from some kind of distribution. And if that's the case, we can calculate the likelihood of our data. And now our goal is to figure out the model parameters that will maximize the likelihood of the data. Okay? And so so the standard approach for when we do linear regression is we say our random noise error, the epsilon sub n, okay, this comes from a normal distribution. Normal distribution centered at 0 with constant variance sigma squared. This is often the assumptions that we're making, and that's why when you check your conditions of linear regression, one of your things is supposed to be homoscedasticity or whatever. Okay, you don't want the random noise to change over time, and that's a thing that's almost always violated, but we just pretend like it's okay and so life can go on. But in real life, it's very this condition is very frequently violated, and we always have to say, well, I don't know if linear regression is even appropriate. Okay, but basically, if the errors come from a normal distribution centered at 0 with variance sigma squared, then Tn, which is basically just the errors added to this thing, then T sub n will come from a normal distribution centered at this thing with variance sigma squared. Okay, so all I'm doing is I'm just saying, well, if this is centered at 0, then the resulting, so this is random, this is not random, right? This component is not random. It's, I guess, deterministic. And so, but if you take this deterministic part, add the random part or the stochastic part, then this part over here will be random, and it's going to follow this distribution, centered it here with variance sigma squared. Okay, and so the idea, this is, sorry for the junk drawing here, right? So when we have, if you see data like this, the idea is, oh, this is even worse. You know, you have this straight line, okay? This is supposed to be the W transpose X sub n, okay? But at each spot, there's like a normal distribution centered at that thing, right? So how do you explain, you know, the amount of scatter that you have in this? I should digitize this thing, but it was like too much work, right? Trying to draw this thing. You know, how do you explain the spread of points that you see? Okay, for this particular location of X, okay, it's centered here. Most of the points will come from here, but because it's random, sometimes you get some high scatter, sometimes some scatter down here, and so you get this, right? And at every different location X, the predicted value, you know, changes along this blue line, and so the values that we see look something like this. Okay, this is okay. All right. So basically, we're just going to say, okay, well, how do we figure out this blue line so that we maximize the probability of the values that we see in here? How do we maximize the probabilities of the values that we see in our data? And that's how we do maximum likelihood estimation. Let me go ahead and give you your first view quiz answer for today, which is the letter D. D as in dog. D as in dog is our first view quiz answer. Right? So we want to figure out the model parameters so that we maximize the likelihood of observing the data we have. Okay, so we will do a quick review of maximum likelihood estimation. And whenever I review concepts, it's always kind of like this high level, a little bit hand wavy, these aren't like formal mathematical proofs. I'm sure if Professor Christo saw my notes, he'd have a heart attack. But we're just trying to get you the big picture idea of some of these things. Okay. All right. So get this. All right. So we're going to say, you know, we have some probability function. The probability function is, you know, what's the probability of getting this particular value, x, for the random variable, if we have some parameter theta, okay? And so here we got, so our probability function has one parameter here, theta. And so here we're going to just have a simple example. We're going to say, you know, pretend in this bag, I don't actually have marbles in here, but pretend I've got a bunch of 10 marbles, right? And in this marble, three marbles are red, the rest are blue. So I got 3 red, 7 blue marbles, okay? And if I'm gonna draw marbles out of my bag, it's gonna come from a Bernoulli distribution, right? It's kind of like flipping a coin that's like weighted so that it lands heads 30% of the time, but this time it's, you know, in the bag I've got 10 marbles, 3 are red, 7 are blue. And I say, well, what's the probability of drawing a red marble? And that would be 0.3, okay? That's not hard. And more formally, if we just say, what's the probability that x equals 1 or 0, 1 if it's red, 0 if it's not, given the parameter 0.3, it's going to be theta to the x and 1 minus theta to the 1 minus x, right? And so that way, if x is 1, it's 0.3, and if x is 0, it's going to be 0.7, and that's our probability function, okay? And so let's say I ask, what's the probability I get this exact sequence? Red, red, blue, okay? Every time I draw it, it's with replacement, okay? Well, because each draw is independent, we just take the resulting probabilities, and so this is going to be 0.3 times 0.3 times 0.7, and we get 0.063, right? This is just the product of each of these individual things for the different values that we got, right? So the sequence red, red, blue is 1, 1, 0, and so that means I need to have this, and if we do this for that sequence 1, 1, 0, we get 0.3, 0.3, 0.7, and we get 0.063, okay? And this one was asking, it's a little bit different from a binomial probability, which would say, what's the probability you get 2 red out of 3 draws, but the order doesn't matter, and then you would take this result and multiply it by 3 because there's 3 possible sequences. But this is the probability function that we're doing. Okay. When we talk about likelihood, okay, this is the distinction between probability functions and likelihood functions. They both describe probabilities, and for a probability function, it's a function of the outcome x, right? We leave the parameter theta as a fixed value, and we alter the x. What x could it be? And the probability function must sum to 1 over all possible values of x if it's discrete, or integrate to 1 over all possible values of x if it's continuous. Okay? Whereas a likelihood function is a function of the parameter theta. Right? We're going to take the observed values, the observed data x, that is treated as fixed. We are not going to alter our observed values, but we change the value of the parameter theta. Okay? So likelihood function does not need to sum or integrate to 1 when you alter all of the values of theta. Okay? So when we talk about this pouch, okay, with marbles, now what we're saying, okay, is we're going to say we've observed, when I drew from stuff from this bag, I observed the observations red, red, blue. Okay? That's going to be my data. My data is red, red, blue, or the sequence 1, 1, 0. But now we're asking, what's the likelihood of the parameters? In that, the proportion, we're asking, what is the proportion that's red inside the bag? And so the proportion could be like, inside the bag I could have like 1,000 marbles, and 999 of them could be red, and 1 could be blue, right? Now that would be surprising because when I drew 3 marbles, I got one of them to be blue. So it would be surprising if there was, if it was 99.9% red, because the fact that I drew a blue marble suddenly would mean like, I can't believe that happened, right? And on the other hand, it could be something else. It could be like, there could only be 100 marbles and only one of them is red. That would also be shocking because I got 2 red, right? So, what's inside here, we want to know, okay? And so unlike the regular probability function back here, okay, x could only take on the value 0 and 1, okay? Over in this function, okay, which is like this part looks exactly the same, okay, because it's kind of the same concept here, except the value that's being altered is the value theta. And theta can take on any value between 0 and 1, right? It's a proportion. So theta can take on any value between 0 and 1. We want to figure out what value of theta will maximize this likelihood. And so when we plug in the fixed values of our observations, red, red, blue, which is the sequence 1, 1, 0, and we say, okay, we're going to do this for our first x. So the first x is a theta, and this becomes 1. And then we have a theta and a 1. And then we have a 0 and a 1 minus theta. The total likelihood of our sequence of data, red, red, blue, is theta squared times 1 minus theta. Okay? So far, so good as far as the likelihood of our data. And so now we want to say what value of theta maximizes this likelihood. So we're going to say the likelihood of our data, 1, 1, 0, for some unknown parameter theta is given by this, theta squared times 1 minus theta. And basically, we want to maximize this function. We want to find the value of theta that is going to maximize this. So what proportion of red marbles in the pouch would maximize the likelihood of observing our data? Okay, and so the way we do this is, well, we just use some calculus. Now, maximizing big products can be kind of tricky because, taking the derivative of a big product, you have all of these product things. So it's a lot easier for us to deal with logs instead. So that's why we often see log likelihood rather than likelihoods, because likelihoods are often a product of a whole bunch of observations. Log likelihoods turn those products into sums. And so we take the log of theta squared 1 minus theta, and so the log of that becomes 2 log theta plus log 1 minus theta. And we're going to say what value of theta maximizes the log likelihood, okay? Because the log is a monotonic function, the value that maximizes the log of the function will be the same value that maximizes the original function. So whatever value of theta maximizes the log likelihood will be the same value that maximizes the original likelihood. So here is the log likelihood, and then to maximize it, I'm going to take the derivative with respect to theta, set that thing equal to 0, solve for theta, and that will be at least a critical value, and then when we check the critical value, that will be the point that maximizes it. Okay, so the derivative of this function, derivative of 2 log theta is 2 over theta. The derivative of log 1 minus theta is 1 divided by 1 minus theta times negative 1. And then so we're going to set this equal to 0, and then we're going to solve for theta. And so this is multiplied by negative 1. I add that over there. I multiply this by theta. Multiply this by 1 minus theta. Gather the thetas together. I get 3 theta equals 2. And I get theta is equal to 2/3. And so this will be the value of theta that maximizes the likelihood of my data. And this kind of matches our intuitive sense. If I drew 3 marbles from the bag, 2 of them are red and 1 is blue, then kind of our guess for what proportion is red in the bag would be 2/3. Okay, and that kind of matches intuitive sense, and when we follow maximizing the log likelihood, we get that. All right, okay. Just want to make sure this is all okay as well. All right, so I'll go ahead and give you your second view quiz answer, which is the letter C. C as in cat. C as in cat. Okay, so with linear regression, we go back to this and we're going to say, all right, if this is my data, my observations come from this normal distribution, can I figure out the W that maximizes this, right? Now, I guess technically there's 2 parameters, theta squared. This variance is also a parameter, but here we're going to just treat the variance as fixed, and we're going to treat our x observations as fixed. We're going to treat the observed values t as fixed as well. Okay, so our observed values t and x, those are going to be treated as fixed. We're also going to treat our variance as fixed. So we're going to just pick some arbitrary number, sigma squared as fixed, and we're going to say let's alter only this vector w, the weights that go into this thing. Can we figure out what values of w maximize the likelihood of our data? So the total likelihood is going to be the product of each of the probability functions, right? So we have the probability of getting this observation t sub n given all of the other values, okay? And if we think about, well, what is this? What is the probability of t sub n? It will be basically your normal density function with mean this and variance sigma squared. Okay, so this is just the normal distribution. So if you think about the normal density, it's this 1 over root 2 pi sigma squared of e to the negative x minus mu squared 2 over sigma squared. Okay, and so instead of mu, we're going to plug in w transpose xn, and that's basically the only difference here. Okay, so we're going to say the total likelihood of all of our data is we're going to say, okay, we're going to take each observation, right? So just kind of going back here, we're going to take the difference between our observed value x and the mean. So our observed value is t sub n minus the mean, according to this, is going to be w transpose x sub n, okay? And then we have all of this, right? I got 1 over square root of 2 pi sigma squared, or I can pull the sigma out. And so this is what we have. It's the product of all of our observations here. Okay. So this is our likelihood of all of the data. I want to make sure I'm not losing anybody with changing all this. So this is all okay. That we're now we have this. So we have this big product, and these are all, each observation, again, the picture way back here is just, when you look at this dot right here, we say, well, what is the probability of getting this thing? Well, it's coming from a distribution centered at this blue line for this particular x, and we say, well, if it's pretty close to the blue line, we say there's a high likelihood, and if it's far away, we say there's a lower likelihood, and it's going to be the product of all of these individual likelihoods, okay? So here we are, and we want to say, all right, can we, treating everything else as fixed, can we figure out the value of w that's going to maximize this? So what do we do? Okay, we have a big product, and we want to maximize this thing. So our likelihood is a function of w. This is the only thing that's going to vary. Everything else is treated as fixed. The variance is a constant. The observed values are fixed. The input values x are fixed. And we want to figure out the w's that are going to maximize this. Right? And I think that's, maybe that's the part that feels a little bit most uncomfortable, is that we're treating our x values as fixed. Okay? And the only thing that's varying is the w. It's a function of w. So again, trying to solve this analytically, we would have to take the derivative, set the derivative equal to 0, and we're going to try to solve for the w where the derivative is equal to 0. And again, because it's a big product, that gets messy. So instead of dealing with the product, we're going to take the log of this to turn it into a sum, and then we're going to set the take the derivative of the log likelihood, set that equal to 0, and solve for w, which is going to be a little bit more easy to solve, I think. Okay, so if this is the likelihood, it's the product of all of the individual probabilities. The log likelihood is going to be the sum of each of these things. Okay, so the log of this is negative 1/2 log 2 pi, right? So this is the square root of 2 pi, okay? And then I've got 1 over theta, so that I get negative log theta. And then this thing, it's e raised to this whole thing, so it just becomes what's inside the e, okay? Or what's inside the exp. And then so this is the sum of from 1 through n of each of these things, and because there's no subscript here, this is the same for all n observations. I can just multiply it by capital N. This is the same for all n observations, so I just multiply this by capital N. These observations change for each of the n observations, so I have to keep the sum here, right? So I have this part, right? And so now we want to figure out the values of w that are going to maximize this entire thing, okay? We're going to find the values of w that maximize this, and we're going to take the derivative, set it equal to 0, and solve. All right, so, whoops. So here we are doing our favorite thing, working with derivatives in vector notation. All right, so I'm going to take, so here's the function just from the previous slide, and we're going to take the derivative with respect to w. All right, so this whole thing is a constant with respect to w, so it's going to 0 out. This whole thing is a constant with respect to w, that zeroes out. And then here I've got t minus w transpose xn squared, and I say, okay, what is the derivative of this with respect to w? Okay, well, the 2 comes down and cancels this out. And so I have t minus w transpose xn, and then we say, well, what is the gradient or derivative of this with respect to w? And it's, applying chain rule. I multiply this by negative x over n, and we take a look at the dimensions, okay, and we want to make sure everything lines up. All right, so this thing needs to be 2 by 1. So if I tried to put this right here, it actually doesn't work out. So the application of chain rule to this requires me to put the xn over here so that the dimensions work out, because x sub n is going to be 2 by 1 for that nth observation. T sub n is a scalar value, and then W transpose xn is 1 by n. So this is assuming your X matrix has 2 columns in it, but you can generalize this to P or K or however many columns you have. Okay, and I'm going to kind of just make the math work out a little bit easier. Next, I'm going to just take the transpose of this scalar value. So W transpose xn is the same as xn transpose W. All right, and then I distribute this, so I get xn tn minus xn transpose W, and this so far works, so far okay. And here it's a summation of all of these things. And okay, so here I am, and if I ask, well, what is what does this all work out to be? Okay, so I've got, so here I am. I got 1 over sigma squared times the summation of all of this. Okay, so if I think about, well, what is x of n? X of n is just one row here. In big capital X, the matrix X, so the nth row in X is just this. The nth observation is this, whereas the matrix X consists of, n rows. So, it's x1 transpose, x2 transpose, et cetera, et cetera, et cetera. Okay? T is just the column matrix of your T's. Your W is your 2 by 1 matrix of weights. Okay? And again, W can be generalized to have more values, and X can also be generalized to have more values as well. But this is what we have. And so if we take a look at this, all right, here I've got 1 over sigma squared, and I've got the sum of this and the sum of this. Okay, I can distribute the sum, right? So here I'm going to say the sum of the xn tn's minus the sum of xn transpose W. And we say, okay, what is this thing? All right, xn transpose, the sum of all n observations in xn tn. Okay, we can say, let's take a look at this. This part right here, xn tn, is 2 by 1. We want the entire thing to also be 2 by 1, right? Because I'm just taking a whole bunch of these 2 by 1s and I'm basically stacking them up and adding them all together. So if I drop the summation and I go from xn to big X, I can have X transpose, big X transpose, which is 2 by n, and T, which is n by 1, this will also multiply out and be 2 by 1. So this works out. And if I do the same thing with this part, xn transpose W, right? So xn is 2 by 1, xn transpose is 1 by 2, and W is 2 by 1. If I expand this, drop the n, so rather than the summation of all of these things, again, each of these things is 2 by 1, I'm going to drop the subscript n. This can become X transpose. This can become X, and the W can just remain W. And if I have X transpose XW, that also is 2 by 1, right? So is it okay going from the summation of xn tn and the summation of xn transpose W to just X transpose T, big X transpose T, and big X transpose XW, right? So this is the derivative, which kind of looks familiar because, well, it's familiar because we've seen it many times before. And so this is the derivative of the likelihood function with respect to W. We're going to set this thing equal to 0. So I've got this. And if I set this equal to 0 and I solve for W, we get kind of what I think we're accustomed to seeing, right? So if I set this equal to 0, assuming sigma squared is not 0, then I can just kind of get rid of it. And I'll have X transpose T is equal to X transpose XW. And then to solve for W, I multiply both sides by the inverse of X transpose X. So I get W hat is X transpose X inverse X transpose T. And that ends up being the same solution that we had earlier, where when we were trying to minimize the sum of squared errors or the mean squared error, we said the values of W that minimize the mean squared error is X transpose X inverse X transpose T. This turns out to also be the values of W that maximize the likelihood of our data. Okay, and part of it gets lost a little bit because you end up with the same answer. So it feels like, why did we bother with all of this if we're just going to arrive at the same answer? There's a few key assumptions that allow this to happen. Okay, and the key here is that we were only able to do the maximum likelihood estimation because we assumed the errors came from a normal distribution or a Gaussian distribution, right? Because we assumed the errors came from a normal distribution, we were able to use this likelihood function, okay? If we did not assume that the errors came from a normal distribution, we would not be able to apply this likelihood function. You need some kind of probabilistic model explaining the errors, and when we do that, then we can apply that likelihood function and we can try to maximize it, okay? And also an interesting thing to note is that the solution of W hat does not depend on the variance, okay? So the variance sigma squared does not show up in the solution at all, and therefore, whatever the variance is, it actually doesn't affect what values of W hat we end up choosing, which is, if you didn't know that this minimized your, the sum of squares residuals, that might be kind of surprising, right? Because if I said, find the value of W that maximize this likelihood, and you see sigma squared in there, you might expect sigma squared to show up in your solution, but it ends up getting eliminated when you say try to maximize this thing. One thing to note, okay, if you look at this and I say, hey, what is the value of W that's going to maximize this? Right? It might not be intuitive that you're going to arrive at the same solution as the values of W that minimize the sum of squared errors. Okay? But if you take a look at this, all right, so this is basically the likelihood, and the log likelihood, we actually see the same components, and that's why we end up at the same answer, right? So this was our likelihood function. This is based on the normal distribution. We said, what is the normal density for each observation? And we said it's coming from this thing. And then when we take the log likelihood, okay, we ended up getting this, right? These end up being constants. This is a negative value. And if you take a look at this part, this is exactly equal to the formula for the sum of squared errors, okay? And so we said we want to maximize the log likelihood. And basically, to maximize this thing with respect to W, okay, or to maximize this by changing W, well, because it's being multiplied by a negative constant, we want to find the W that's going to minimize the sum of squares of error, okay? So if we minimize the sum of squared errors, it gets multiplied by a negative value, and that's going to end up being the same thing that maximizes the log likelihood. So it ends up working out. But again, this relationship only holds if we assume that the errors are normally distributed. Okay, because if the errors are not normally distributed, then this likelihood function does not apply. Right? This likelihood function of e raised to the basically x minus the, it just so happens that Gaussian distributions, you're looking at, x minus mean quantity squared, okay, e raised to that thing, right? And that's kind of like saying, let's minimize the sum of squared errors. But if you had some kind of other error function, right, if you say the errors are uniformly distributed, well, actually, that's going to kind of end up being this. Well, if you have some other thing, it might not necessarily be the case, okay? So this is kind of a thing that, we end up going full circle, ending up back at the same result. But here's a slightly different approach where we are trying to maximize the likelihood by altering W, and we end up getting the same results, okay? And again, it feels a little bit wasted because we already knew this answer, right? But by taking a maximum likelihood approach, now we can start bringing up other things, talking about the variance of our estimates and taking a look at that. So we'll take a look at some other components in our solution on Wednesday and Friday by taking a maximum likelihood approach, which is, even though right now it's the same answer as minimizing the sum of squared errors or mean squared error. All right, let me go ahead and give you your last view quiz answer for today, which is the letter A. A as an apple. A as an apple is your last view quiz answer for today. All right, we'll wrap it up for now. We'll see you all on Wednesday. Have a good rest of your day.